let's start talking about the objects in our solar system, with first, the Sun. So the Sun is actually a star. The Sun is the star that is the very closest to the Earth. In fact, it is because of the Sun's energy that the Earth has the nice habitable conditions that it does. The Sun is made of mostly hydrogen, about 74-ish% hydrogen, and 24-ish% helium, with the rest being made up of everything else. Now, the Sun is so hot that it's actually in a plasma state. What a plasma is it's very similar to a gas, except the atoms are not neutrally charged. The atoms have actually had electrons removed. So a plasma is actually made up of a whole bunch of free charged particles. Other than that, it behaves pretty much the same as a gas. Now, the hydrogen in the core of the Sun is actually fused into helium. During that process, a little bit of matter is turned into energy, which is how the Sun produces its energy. The Sun creates energy through thermonuclear fusion, fusing hydrogen into helium. Now, if you remember, we talked about E equals mc squared, energy equals mass. This shows that we can actually convert from one to the other. So as the Sun is converting mass into energy, that energy is then being radiated away. So every second, the Sun actually converts 4.5 million tons of mass into energy. Now that is a very, very large number, but the Sun is even bigger. So what this means is, although technically the Sun is losing mass every second because it's radiating the energy away, we don't really notice that much of a change because of how massive the Sun is. The Sun has three different zones in its interior. At the very center, we have the thermonuclear core. This is the region that has the pressure and temperature to actually convert hydrogen into helium. Surrounding the thermonuclear core, we have the radiative zone. The radiative zone is a region where the energy is escaping as radiation, meaning as light. Now, there's still lots and lots of material here, but in this case, it's actually light trying to break free of matter is how the energy is going through. Then the last layer is the convective zone. In the convective zone, the energy is being transported through convection. We actually produce these convective cells, and then it finally reaches the surface where it's able to radiate away. Now, the fusion in the core happens at a very high temperature. The current temperature of the core we believe to be somewhere around 15 million Kelvin. In other words, it's really, really hot. Here is our second question. Strictly speaking, in every second that passes, the mass of the Sun, A, decreases, B, remains constant, C, increases, or D, reinvents itself. Go ahead and think about it, and we'll discuss in just a bit. All right, so in every second that passes, the Sun converts mass into energy, and then that energy is radiated away. So what this means is, strictly speaking, the Sun is decreasing in mass. However, when we compare the amount of mass that's being turned into energy, it's actually a very, very small fraction of the Sun's total mass. So although it is technically decreasing in mass as it converts matter into energy through thermonuclear fusion, it's not actually that noticeable because it's such a small fraction of its total mass. So on to the inner planets. So again, the four inner planets are Mercury, Venus, Earth, and Mars. That's starting with the one closest to the Sun, going to the one farthest from the Sun. All of these have relatively high densities and are made of rock and metal. As we look at how fast it is that these planets orbit, we see that Mercury orbits the fastest, and then it decreases with greater distance. So Mercury orbits the fastest of these planets, and Mars orbits the slowest. This is actually true for all planets. The farther away the planet is, the slower that it is orbiting. This is known as Kepler's third law, named after the astronomer mathematician who actually figured it out in the 1600s. Mercury is the planet that is the very closest to the sun, and it's actually just a little bit larger than our moon. In fact, it has a lot of similar characteristics to our moon. Neither our moon nor Mercury has an atmosphere, or at least nothing that we would normally consider an atmosphere. Both of them are very heavily cratered, indicating that there is no geologic processes to renew their surfaces. However, one big difference is temperature. Mercury is much closer to the sun, which means that it gets a lot hotter. During the daytime, it can get up to around 430 Celsius. However, because it has no atmosphere, during the night it also gets really cold, down to negative 170 Celsius. It takes Mercury about 88 days to complete one orbit around the sun, and although it is close to the sun, it is actually rotating very slowly. 1 day on Mercury, one complete rotation on its axis, is 176 Earth days. Venus is the second closest planet to the sun, and I've heard it referred to as the Earth's sister planet, in that they're both very close in size. Venus is actually just slightly smaller than the Earth, at about 95% the Earth's diameter. One big difference between Earth and Venus, there's actually a lot of big differences, but another one is that the Venus has a very thick atmosphere. Its atmosphere is about 95 times the atmosphere of the Earth. What that means is the surface pressure from the atmosphere is 95 times greater. The atmosphere is literally crushing. The atmosphere on Venus is primarily made of carbon dioxide, which actually leads to an extreme greenhouse effect. The surface temperature on Mercury is around 460 degrees Celsius, again because of that greenhouse effect. Although Venus is not the planet closest to the sun, it is the planet that is the very hottest because of that greenhouse effect. It is even hotter than Mercury. Because of the thickness of its atmosphere, this 460 degrees Celsius is actually true everywhere all the time. It's not hot on the day side and cold on the night side. It is hot everywhere all the time. This is the equators, the poles, the day side, the night side, everywhere all the time. Now, we have seen many volcanic features on Venus, indicating that it is likely volcanically active, and we see some evidence of some type of tectonics. It is not plate tectonics like what we see on the Earth, but we do see that the crust has been shifting around. Venus takes about 225 days to orbit once around the sun, and 1 day on Venus is the same as 117 Earth days. Another notable weird thing about Venus is that it actually rotates backwards compared to all of the other planets. So on the Earth, the sun rises in the east and sets in the west. On Venus, the sun rises in the west and sets in the east. Another kind of interesting point of Venus is that it does have cloud layers. However, the clouds on Venus are not made of water like the clouds are on Earth. They're actually made of sulfuric acid. Venus is a terrible place. Don't go there. The Earth is the planet that we've talked about the most. Pretty much everything we've discussed in geology has been about the Earth. One nice thing about the Earth is it's in a region that we refer to as the habitable zone. The habitable zone is the distance from a star where you get enough energy where water can be maintained as a liquid. So the Earth, having lots and lots of oceans, means that we're right nicely positioned within the habitable zone. Mars is the fourth planet from the sun, and it's the last of the terrestrial planets. It's a little bit larger than half the Earth's diameter, and it has a very thin atmosphere. So Venus's atmosphere is 95 times thicker than the Earth's. Mars has an atmosphere that's very thin. It's about 100 times thinner than the Earth's, although it is predominantly carbon dioxide, somewhere around 95% carbon dioxide. The equatorial regions, which are the regions that receive the most sunlight, have temperatures that range from 30 degrees Celsius during the day to negative 130 Celsius at night. This extreme temperature change happens because of its very thin atmosphere. So both Mercury has an extreme temperature change because it has no atmosphere, and Mars's atmosphere is thin enough that it doesn't do much to help the change in temperature. Whereas when we compare that to Venus, because of how thick Venus's atmosphere is, it's always incredibly hot all of the time. Currently, there have been many missions to Mars trying to study it and understand what's going on. One of the very interesting things that we have learned from all of these missions is that it is very likely that Mars actually had liquid water at one point in the past. And not just a little, we show evidence of large amounts of liquid water, entire oceans. Now, the reason why we're interested in liquid water is for the possibility of life. There may have been life on Mars at some point in the very distant past. Today, we have no evidence of any liquid water because of changes to the Martian atmosphere and overall climate. Mars is small enough that it has actually been losing its atmosphere. And as it loses atmosphere, then we get less and less greenhouse effect, and the whole planet has slowly frozen over. So any water that it used to have has now been locked away either in the polar ice caps or as permafrost in the ground. And without liquid water, there is no life. So we don't currently believe that there could be life on Mars, but there's a possibility that at some point several billion years ago that maybe it did have the conditions that were right for life. This is actually an ongoing question. There's a lander that is going to be launched this year. The working name for it was the Mars 2020 rover. I believe that it has now been given an official name, Perseverance. And one of its primary missions is to actually determine if there was life at one point in the distant past on Mars. 1 year on Mars is about 1.88 Earth years, so its year is longer. And one Mars day is actually slightly longer than an Earth day at 24 hours, 38 minutes. Here we see a picture of the Curiosity rover. This was launched to Mars in 2012, if I remember correctly, and it's actually still going strong. The primary mission for Curiosity was to determine if there was liquid water in the past, and therefore if the conditions were right for habitability. Could there have been life in the past? And currently, all of the evidence says yes, that the conditions may have actually been right at some point in the very distant past for Mars to have harbored life. Again, I want to stress, we do not currently believe there is life on Mars, but we have evidence that Mars may have had life at one point in the distant past, around 4 billion years ago.